Okay, so the last but not least talk in this session is about incremental shortest path in almost linear time via modified interior point method by
Yeah, thanks for the intro. Yeah, as you heard, I'm talking about incremental shortest paths. Let me start by introducing the problem. The problem is, as the name suggests, the goal is to find shortest paths from a given source vertex in a graph that undergoes edge insertions. In this talk, we're going to focus on approximate shortest paths. Later, I'll talk about a little bit about why this is like the correct thing to look at. Okay. Just to give a pictorial representation, you start with some graph maybe, then over time, edges get added to the graph, and you just want to maintain what the shortest paths are in the graph. Yeah, with approximations. Good. There's a natural analog that I'm not going to talk about, but just for motivation, it's useful to also think about the decremental shortest paths problem, which is the same problem where you start with some graph, and you want to maintain approximate shortest path distances as edges get deleted from the graph instead of inserted. So this is kind of like it's an analogous problem with edge deletions instead of insertions. Okay. In terms of why approximate shortest paths instead of asking for exact shortest paths, I think there's two reasons. One is that approximate shortest paths are often more than enough for a lot of algorithmic applications. For example, decremental single source shortest path, it's usable in like multiplicative weight frameworks for a lot of algorithms for flows. For example, Gar Kahneman developed a Maxwell algorithm based on decremental shortest paths. And additionally, there's actually hardness against kind of like any like slightly strengthened version of this problem, which I'll go over on the next slide. Okay, so there's this conjecture called the online matrix vector conjecture, and this rules out exact incremental or decremental shortest paths, even between a single pair of vertices S and T. Additionally, you can, well, yeah, so that's ruling out incremental and decremental. Now you can ask about fully dynamic. What if I allow edge insertions and deletions? Then you're still in trouble because fully dynamic edge insertion deletions, shortest paths, that captures reachability, but again, there's hardness results against reachability, and reachability is kind of like an infinite approximate shortest path. So for like, also in this like hardness landscape, it also makes sense to focus primarily on approximate shortest paths in partially dynamic graphs. In other words, those only undergoing insertions or deletions. Just to give a little bit of a recap onto previous works in this direction, one of the first works studying dynamic shortest paths was this work of Evan and Shiloh, which gave an exact BFS tree, let's say in unit weight graphs, in total time m times n. Since then, well, there's been a lot of work on dynamic shortest paths in a lot of different regimes, but I'll focus on the incremental version, 1 plus epsilon. And there's runtimes of n squared, m to the 5/3, and the current state of the art, as far as I know, is something like m to the 3/2 or m to the 4/3 time. And this is some work a couple years ago. In this talk, we're going to talk about an almost linear time algorithm, which is m to the 1 plus little o of 1. But before stating the result, I want to talk a little bit about what it, like some context and maybe some difficulties towards getting this. Okay, good. So some context for the algorithm is that while the algorithms on the previous slide were primarily combinatorial, they're kind of based on hop sets or like other kind of notions like that. The approach that people started taking for these dynamic graph problems in recent years is based on continuous optimization. Starting point is the almost linear time algorithm of some co-authors and I for Maxwell and min-cost flow based on an interior point method. Okay. After that work, later works realized that it's like this like algorithm takes several steps, right? These later works realized that you can kind of amortize the steps of this algorithm over the course of edge insertions in a graph. So like imagine that like this first algorithm in the first line takes like m steps. If you do some extra analysis, it turns out that over the course of edges being inserted to the graph, the algorithm still takes m total steps over the course of all the edge insertions. So you get no runtime slowdown, even over a partially dynamic graph. And for this, out of this, you got like a bunch of almost linear time algorithms for min-cost flows in partially dynamic graphs. Okay. And as applications of this, you get things like incremental cycle detection, SCCs, incremental decremental flow problems, etc. And also, if you treat an ST shortest path as a min-cost flow problem where you have one unit, where you want to send 1 unit of flow from S to T, this tells you that I can find an ST, I can maintain an ST shortest path, let's say in incremental graphs, in almost linear time. But again, this is single source and single sink. So now how does this relate to single source shortest path? Well, again, ST shortest path is 1 unit of demand, so this is captured by prior works. On the other hand, in single source shortest path, you care about a demand from S to every other vertex. Like you care about a bunch of pairs, so you can't just run this algorithm for all pairs. That wouldn't make any sense. However, it is known, if you can check that if you initialize the following demand, which is n-1 units at S and -1 units at every other vertex, that if I ran an exact min-cost flow for this, the minimum total length is exactly the sum of the shortest paths. So kind of like what you can do is you can take all the shortest path demands, add them all on top of each other, and it is possible, well then you do get the shortest paths in the exact setting. However, the issue is that this breaks down when you consider approximations. Imagine I had an algorithm which was initialized on this like n-1 demand, and I was able to maintain the value approximately. This doesn't actually help you get every single shortest path distance approximately, because maybe just like some fraction of the vertices have a large error while the other vertices don't. So kind of the context is like, you can start here, but how do you handle the vertices where like there might be a large error? Okay, so the main result is that in an incremental graph undergoing edge insertions, we're able to give an algorithm that runs in almost linear time and maintains an approximate shortest path for every single vertex where the total runtime is m to the 1 plus little o of 1. And also the algorithm supports maintaining a shortest path tree and path reporting. Okay. So now for the remainder of the time, I'll just give some very high level picture of the algorithm and then conclude. Okay. So the first step, as we discussed, is to view SSSP as the following demand. You want to send n-1 units out of the source and 1 unit into each of the other vertices. So now the optimum is exactly the sum of the shortest path lengths. And kind of what you're going to do is you're going to run this interior point algorithm amortized over edge insertions and just keep running it and see what happens. The idea is that when you're running this interior point algorithm, at some point the algorithm will say like, it's going to halt and say like, I don't want to make any more progress after this edge insertion and I want to wait until the next one. In this case, what you try to do is use some duality argument to extract out potentials, like the potential, like Johnson potentials for shortest paths. For example, like the potential was satisfied that the potential is the most of the shortest path length, but the sum is approximately the truth. And then I want to recurse on vertices where the potential is much less than the true shortest path distance. And the reason that this makes sense is because those are the vertices where the shortest path length might have gone down. If phi is close to the distance, then the distance didn't go down. But if it's far away, then it might have gone down a lot. So, okay. That's just the high-level algorithm idea. The main difficulty here is how you actually get access to these dual potentials. Because like the algorithm is kind of operating in flow space. You're maintaining a shortest path flow at every time, but you somehow need to get access to these potentials. So this is kind of the main point I'm going to try to get across if I can. Cool. Okay, so just to get in the mode of trying to like understand what the algorithm is doing a little more, let's do one quick reduction. In this reduction, let's work at a fixed distance scale. Let's only focus on getting shortest path distances right if they're between some dyadic range L to 2L, and let's ignore the rest. Okay. And kind of like for this dyadic scale, initialize a phase, and a phase ends when the sum of the lengths has gone down by some 1 minus alpha factor. By like detecting when a phase ends can be done with the interior point method, dynamic interior point method. Okay. Now, during this phase, I want to detect vertices whose shortest path length has went down by a lot, by 1 minus epsilon factor. And you can check that the number of such vertices is alpha m over epsilon by like a Markov's inequality argument. So if an algorithm was able to report these vertices up to a little bit of loss, then you can recursively process these vertices to like try to get their shortest path lengths correct. Yeah. So again, the idea is try to like detect detect vertices whose shortest path length has gone down, and then recursively process them. Okay, so the next point now is how do I detect when a vertex has had its shortest path length go down? The idea again is to try to do these dual potentials. So you're running this interior point method, and at some point you want to get access to some dual potentials from the fact that the interior point method can't run anymore. However, this is a little bit difficult to do directly. So in this paper, what we do is we add dummy edges from the source vertex to every other vertex v, whose length is initialized as the initial shortest path length, d of v. So just have a picture. Initially, you have some graph. We're going to add in these dummy edges from the source to every other vertex. And these edges kind of have some, like the edges are weighted just like what the initial shortest path length is. So because they're weighted that way, they don't change any actual shortest path distances. But the benefit is that if you take the dual linear program, the potential difference across that dummy edge is exactly the potential of v, phi of v. Because the potential is phi v minus phi s, but in this dual approach, phi of s is 0. So just phi of v. And the idea behind this is that by adding these dummy edges, you are able to use properties of that edge in the interior point method to get access to the potential. So that's kind of like the first trick. And the second trick is a slightly more technical point, which is that if you use this first trick and you set it up, these potentials phi, they can change over time. So like you might worry that an edge initially has some potential phi and it goes down and up over and over and over. And then this means this edge goes like back and forth between being like dangerous, as in like phi is too low, and it not being dangerous. And this can happen up to m times. But our goal was to get a bound of alpha times m on the number of vertices that, like dangerous vertices instead of m. So the technical idea in this paper is that when you set up the interior point method, instead of having a logarithmic barrier on these dummy edges, you add a high-powered barrier on these dummy edges, x to the minus p. The idea is that this high-powered barrier penalizes movement much more heavily than the logarithmic barrier. And if you do the analysis, it turns out that this high-powered barrier penalizes movement exactly by a factor of an extra 1 over alpha, and thus you save an extra factor of alpha in terms of the number of changes that can happen on these dummy edges. So overall, the number of vertices that can become dangerous over time is alpha m over epsilon. Just wanted to say a couple more words about this high-powered barrier. So as in a standard interior point method, it uses this thing called a self-concordant barrier, like negative log x. However, this high-powered barrier, x to the minus p, is not self-concordant, and thus standard interior point method analysis does not really say anything about whether this algorithm should work. So in this paper, we have to do kind of an ad hoc method to argue that this algorithm works specifically in the case where you're adding this barrier only on the dummy edges and not on the other edges. So it's a little bit strange, but I think this is maybe like a direction for future research, like what properties in general make it possible to add these powered barriers in this setting but not in other settings. Cool. Okay. So yeah, overall we gave a near linear time algorithm, almost linear time algorithm for approximate SSSP and incremental graphs. The main ideas were to like reduce to reporting vertices whose length decreased, and we do this by adding a high-powered barrier onto some dummy edges that we added. In terms of future directions, I feel like one very natural future direction is whether any ideas here extend to decremental shortest paths, and then whether we're able to use decremental directed shortest paths for more graph algorithms problems in the future. Because I feel like there should be a lot of applications, even though, yeah. I mean, the main bottleneck might be that just that we don't have any decremental shortest path algorithms yet. And then, of course, can this m to the little o of 1 and this epsilon dependence be improved? And I think maybe like an interesting point is like, just like to study this high-powered barrier more. Like, are there other settings where it can be used? Things like that. Like, what made it possible that it could be used here to some benefit, but it hasn't really been seen anywhere else? Okay. Yeah, so that's all I had. Thanks.
Any questions to Jan?
I just want to be clear, your algorithm maintains explicitly shortest path tree.
I believe the algorithm can maintain the shortest path tree, or like basically something like a shortest path tree. Yeah, it might not be a subgraph, but like it basically is a shortest path tree. Yeah, yeah. Sorry. Maybe just one more sentence, which is that like there should be there should be basically a black box reduction from maintaining maintaining a superset of vertices whose distance went down to maintaining a shortest path tree. The idea is kind of like you maintain an initial shortest path tree, and then you look at the vertices whose distances went down, you contract away everything that stayed, and then recurse on that. So like basically it should maintain a shortest path tree. Yeah. Good. Good. Okay. Yeah. Sorry. So, yeah. Sorry. The dependence on epsilon's kind of bad. Like that's what I might have stayed on the main theorem side for not long enough, but technically, I guess the dependence on epsilon is like quasi-polynomial or something like that. It's like a little bit worse than polynomial. So I think that's maybe that's what I meant by the improved epsilon dependence. Yeah.
Any other questions? Yeah.
So sometimes in these settings like multiplicative weights, you want some representation of the past. So you can do weight updates or something efficiently. Is it hard to pull out that from this kind of distribution? That makes sense.
Yeah. So as Chachapan was saying, asking you basically it should be able to maintain a shortest path tree. Yeah. Sorry, it should be basically able to maintain a shortest path tree that changes a total of like m-ish times is the proper statement. Yeah. So then you can kind of do whatever you want with it at that point.